So, lecture 14. Let's continue on from where we were before, where we were last time. Let me just start today with just some remarks. So, I want to just make some remarks. These are already included in the notes regarding maximal regularity. So I feel like I didn't make certain things clear. So the first remark I want to make is in condition 1, I said something like U is in L2 of 0 tau naught dom t when tau naught is finite and tau naught is less than or equal to tau. So the point here is that this is saying that the integral 0 to tau naught of u of t plus t u of t for each tau naught. That's finite. But we cannot conclude from this that we know the integral 0 to tau is finite when tau is infinity, right? So for tau equals to infinity, we cannot conclude that the integral 0 to infinity of the ut dom t norm is finite, obviously, right? Because, I mean, when tau naught is finite, it's just saying that this integral converges for each tau naught that's finite. Okay, so that's something I want to emphasize. The second thing I want to emphasize is a little fib that I said. So I said that the maximal regularity comes out of the H infinity functional calculus. That's actually strictly not true. So the reason I presented it in this way is because in order to do all of these boundary value problems, we need a H infinity functional calculus in general to begin with, because that's how we can really prove the trace theorem. However, when we have a Hilbert space, we just need to assume that T is injective omega sectorial for omega less than pi on 2. And the reason for that is that under this hypothesis, we actually get z mapping to e to the minus zt is holomorphic for z in the open sector pi onto minus omega. Actually, pi onto minus omega minus some small epsilon for epsilon positive, right? So for all epsilon positive. Okay, actually, no, we don't need the epsilon positive, I think. Well, I'll just leave it there for epsilon positive. So, so for a slightly smaller angle than pi onto minus omega, we actually have that this is holomorphic or analytic, and that's enough to guarantee the maximal regularity for a Hilbert space. However, for a Banach space, we need, as I said before, these so-called bounded imaginary powers, right? So, i.e., we need e to the t to the is of u, t to the is is bounded by some constant c, and e to the, or some, I think I called it k, e to the s modulus theta, right? So we need bounded imaginary powers to guarantee maximal regularity. But the point is that a H infinity functional calculus implies bounded imaginary powers. So, I mean, this is the reason I expressed it in this way. The reason that I actually wrote these considerations in this way, because we always have a H infinity functional calculus, and that's what's needed in general. But in this particular setting, we don't need that, right? So I just thought I should emphasize that. Okay, so let's continue to move on and try and finish this section on these regularity problems. So from next time onwards, we can consider general operators and move away from the model problem. So to begin today's lecture, I'm going to start with a lemma. That lemma characterizes the Sobolev space HK Z rho closure E. So what is this characterized as? So this is equal to the intersection of L equals 0 to K, the domain of the operators partial T K minus L modulus A to the L, and with, so this includes with the Sobolev norm being comparable, I should say squared, this is comparable to L equals 0 to K partial T K minus L modulus A to the L of U squared. So this is not so hard to believe. I mean, A is a order 1. So A is a first order differential operator, and so modulus A, and it's on a manifold without boundary. So we're on the cylinder still, and so we expect that the Sobolev space is the measure of the derivatives in this partial m direction along with the partial t direction, right? The transversal direction. So this should not be a surprise. So I won't prove it. I'm just gonna leave it at that. So why do I want this lemma? Well, the main thing we want to prove today, or one of the main things, is the following. So let's recall that we define this S naught of U of t as equal to what? So this was 0 to t e to the minus t minus s modulus a chi plus of a u s ds minus and t to rho of e to the minus how did it go? It was e to the minus where do I have it? I had it somewhere here. Sorry, just give me a second. Just don't want to get it wrong. So, well, let me instead of writing it like this, let me write it in terms of the generators, because that's what we want to use anyway, right? So let's write it in terms of the generators. So this was W of t chi plus of a of u minus w rho minus t of chi minus a, now with this c rho applied to u, right, which is this coordinate transform, remember, where c rho of u of t is equal to u of rho minus t. So A throughout, everywhere, is always the adapted boundary operator. That's consistent. The adapted boundary operator has nothing to do with T. Well, that's an application. This is an operator application. This is the composition of operators. I'm not deriving it by t. I mean, partial t is a differential operator. Modulus A is also built out of a differential operator. It's a composition of a differential operator with a signum. Yeah, so there's no derivation of the A with t here. This is just operator composition. It's like partial ddt composed with partial ddx. Okay. So let's recall. So is everyone okay with that? I mean, is there some issues with what's going on here? So maybe I need to recall that, you know, z rho bar is equal to 0 to rho closure partial m, and A is well, it's an unbounded differential operator on partial me to L2 partial me, right? So this is the domain of the operator. Right, so now when I'm looking at HK of this space, I'm really looking over this cylinder, right? So I can apply, I mean, these are going to be, so sections here in the HK are going to be of the form U of t, and for each U of t, I'm going to be landing in the bundle E, or E restricted to partial M. Okay, anyway. So what's the main lemma here? So the lemma is that this operator S naught maps HK of Z rho bar E to HK plus 1 Z rho bar E boundedly with bound independent of rho. Okay, so that's a very, very fundamental point. Okay, so let's first start with the case k equals 0. So the case k equals 0. Okay, so what happens here? For the case k equals 0, so let's so from the lemma that we have here, we see that the norm, the H1 norm, can now be written. So maybe I'll just write it explicitly. So V equals H1 Z rho bar of E. If then the H1 norm is comparable to, in this Z rho bar, is comparable to the integral 0 to rho of partial TV squared L2 of partial M plus this estimate, this integral, right? So modulus A V squared, oops, there's a dt missing here, dt, L2 partial M dt. So this is boundedly. Maybe just bounded. Yeah. Boundedly. Okay. So now we want to explore what happens if we set V equals to S naught of U, right? So for let U be in L2 of Z rho E, and let well, this is not, so strictly speaking, this is not the right way to do it, right? So we should really do it by density so we can actually compute the norm, right? Recalling that C infinity, because Z rho bar is a compact manifold, but with boundary, So C infinity is still going to be a dense subset of this space, is dense in HK Z rho bar of E. Let U be in, and this is for all K, right? So this is for all K. So let U be in C infinity, and so we compute the S naught naught, the S0 naught, and V equals S naught of U, right, and compute. So let's have a look. So that from the previous estimate, we have S naught of U H1 squared is comparable now to 0 to rho partial T S naught of U. Okay, well, it's unfortunately a long expression. Okay, so plus, well, squared plus modulus A V squared dt. So that's going to now be bounded by, so taking this form, so just recalling this, so remember W is the generator for the inhomogeneous Cauchy problem that we solve, right? So S naught generates these solutions, and remember that it's an inverse on one side. So now we have this being bounded by what? So 0 to rho of partial T WT chi plus A of U squared. And these are all L2 norms now, right? So I won't bother writing out the L2 part. dt plus 0 to rho dt, modulus A W T chi plus of A of U squared dt plus plus 0 to rho now of the other term, right? So WT, rho minus T chi plus chi minus of A U squared dt plus 0 to rho modulus A omega rho minus T chi minus A U squared dt. Okay, so what does maximal regularity tell us, right? So maximal regularity now tells us that the partial T of this omega, so remember the chi plus is the initial value for this inhomogeneous problem, right? So the maximal regularity estimate precisely tells us that this first term is bounded by chi plus of A of U. And similarly for the second term, right? So what we obtain immediately from maximal regularity, so this is maximal regularity, is that the first term now zero of U, what? C rho, yes, sorry, yeah, it's 0, yeah. Okay, sorry, so that's right, so this should be C rho of U, C rho of U, right. Okay, so what maximal regularity then gives us is the following. So it gives us the integral 0 to rho of chi plus of A of U squared. So that's from the first term, dt, right? So there's a ut here now, right? So chi plus gets applied to each ut, right? So this is a ut here, squared dt. So I've omitted that from well, actually the t dependency here is clear, right? So the w has a t in it. So maybe these integrals, well, this integral here maybe should also contain the t, just to really emphasize that it's been applied pointwise, right? So we have this plus, now we have 0 to rho of can work that out. That's quite easy to show. So it commutes with the chi minus of a, and it's also an isometry of this interval 0 to rho, right? It's just integrating backwards rather than forwards. So then this is now equivalent to 0 to rho of chi plus of a of u of t squared plus chi minus a u of t squared dt. But the chi plus and the chi minus are projectors, okay? And one is the complementary projector of the other. And that precisely means that inside this integrand, for each t, we can reconstruct u. They're not orthogonal projectors, but they're projectors. Good. So what is this? This is precisely now the L2 norm in Z rho bar E of U. So this shows that S naught, so on this dense subset, S naught maps, on this dense subset C infinity, we have the required estimate. So by density, we obtain that S naught maps L2 of Z rho E to H1 of Z rho E. Okay, so it boosts up regularity. Okay. All right. So similarly, we can try and do this for the higher order case. So for the higher order case, so for k greater than 0. Okay. So let's just take some f now in the sublove space HK, or I should say the domain of modulus a to the power of L, which through various considerations, I mean, this is really a consequence of elliptic regularity again, but applied to a slightly general context, we have that the domain of a to the power modulus a to the power of L is actually the sublove space HL. And so for such an f, when we differentiate the solution generator, what do we get, right? So let f be in there and then differentiate solution generator, or the potential, whichever one you want to call it. So what do we get? We get two quantities. So we get partial t to the L of WTF. So this is going to be, if we apply it repeatedly, we get minus 1 to the power of L, W T A to the modulus L of F, plus, now we take the sum of m equals 0 to L minus 1, partial t L minus 1 minus m, modulus a to the m f of t. And if we do the same thing for the rho minus t, of f, then we get minus 1 to the L plus 1 of w rho minus t, again a to the L of f plus m equals 0 to L minus 1 partial t L minus 1 minus m modulus a to the m f of t. Okay, so why does this happen? So remember that so why is this true? So let's just recall why this is true, right? So remember that w partial t of wt f plus modulus a wtf. So this is the problem that we're solving, right? This solves this inhomogeneous Cauchy problem. So also so using these basic facts and knowing that if we're in the domain of the operator, we can commute the operator across this finite integral, it's not hard to actually just work out these two formulas, right? So I'll leave it as an exercise to verify these two formulas, but they are really the most important facts here. Okay, so what we want to show, so we show, so again by density, assume that u is in C infinity partial me. Okay, so it suffices to show, so by lemma, by previous lemma, that is the form of the Sobolev norm inside this. Well, you can think of it as maybe a coordinate system with respect to the operator A. So by this previous, yeah. So okay, so by the previous lemma, sorry, I lost my train of thought. So okay, so by the previous lemma, what we need to show, it suffices to show that when L is in 0 to k plus 1, partial TL modulus a k plus 1 minus L W F in L2 Z rho bar is now bounded by the HK norm of Z rho closure rho bar. Okay? All right. So for L equals to 0, right? So for L equals to 0, what we have is we need to show A modulus K plus 1 W F L2 Z rho. So this, I mean, again, as I said, so the W is, so maybe I'll write it out explicitly. So what's this? So this is going to be well, maybe actually I'll okay, maybe I'll just write this out first. So note that A to the L of W T F is what? So this is equal to A to the L of the integral 0 to rho e to the minus t minus s modulus A of f of s ds. Okay? So what? So actually this means that I mean, this is why we want to have a functional calculus, because one of the most important facts that come out of a functional calculus is that we get nice commutativity of operators within the functional calculus, right? So now if f is in, so for I mean so here this is for this range of L 0 to k plus 1, or maybe 0 to k, right? So and we assumed that f would maybe be in the domain, I should say f here, sorry. So assume f is in C infinity. And actually, not C infinity of partial m, this should be z rho bar. So now f is smooth enough so we can push the operator through, right? So we now have e to the minus t minus s, because the semigroup is in the functional calculus, is a finite integral, so we have commutativity here, and we have this being a to the L f of s. Actually, that's not what I wanted, sorry. Let me, L minus 1, I want to keep the modulus a here. Okay, so what is this now? So this is exactly equal to wt a to the L minus 1 applied to f. Okay, so we can push a through w, right? So that's a very important fact. So now let's look at the case of L equals 0. So for the case of L equals 0, we have a modulus k plus 1 w f squared, and we're taking this in L2 z rho bar. And this is now equal to modulus a w, sorry, there's a semicolon there, a to the k of f, L2 of z rho bar. And of course, we have maximal regularity again, right? So we through the maximal regularity estimate, this is going to be modulus a to the k of f, L2 of z rho bar. And of course, now this is going to be bounded above in the HK norm of f by the lemma, right? So this is previous lemma. Okay, so that's the case for L equals 0. Yes? Yes, sorry. Of course you have to have the modulus A, right? And that's the expression that we have here in this line. And then the way we get from here to here is because we have this maximal regularity estimate, right? The maximal regularity estimate bounds the t derivative of w plus the norm of the t derivative of w plus the modulus A acting on w by the initial data. And the initial data now is modulus A to the k of f, and that, as we said before, is bounded by the HK norm. Okay, thank you. Thanks for pointing that out. Okay, now for the case of L greater than or equal to 1. So by what we have upstairs, the star, we just multiply, right? So that's the star here. We multiply by modulus, so we multiply just this partial TL expression by modulus a k plus 1 minus L, right? So we multiply this by modulus a k plus 1 minus L, okay? And then what do we find? So we find partial T L modulus a k plus 1 minus L WTF, and that's going to be what? That's going to be now, we push this onto the to this left hand side here. So we have a modulus a to the L here. So so then this is going to be equal to -1. We keep the modulus a, wt modulus a to the power of k, right? So I keep 1 by, we multiply this by something. Sorry? Oh, sorry, multiply star by this, by modulus a k plus 1 minus L. Yes? Okay, so the point is that we had a modulus a to the L here, and that gets killed off by this, and we keep 1 power of the a here. Good. So that's that. And now we have this sum, right? M equals 0 to L minus 1. Now we have partial t L minus 1 minus m modulus a k plus 1 plus m minus L f of t. But the point here is that this is really the lower order term here is just it's a lower order norm, right? So so what's it going to at most add up to? At most it adds up to order k, right? So it's right. So well, let me write this out. So then what's the estimate? So the estimate well, I don't have this, L2 Z rho. So this is going to be less than or equal to, so well, maybe I'll write that here. This is less than or equal to norm modulus A W T modulus, oops, there's an F here. Maybe I'll get rid of the T's and just put dots here. Modulus A to the K of F, which we know how to bound, L2Z rho, plus, so plus sum m equals 0 to L minus 1, partial t L minus 1 minus m, modulus A to the K plus 1 plus m minus L of F squared L2 of Z rho bar. Okay, so both of these now, so the first term is again maximal regularity, and this tells us that we have modulus A to the K of F L2 of Z rho bar plus now this. So this is at most bounded by the HK norm, so we have the HK norm of Z, oops, there's a squared there that shouldn't be there. Okay, good. And now this is now going to just be bounded by the HK Z rho bar norm. Okay, so so what does this prove? So this then shows us that so we can finish the proof as before now, right? So similarly for W C rho dot F, right? And noting that C rho is bounded HK to HK. And then we can just finish the proof, right? So to finish proof, when U is in C infinity Z rho E, we have the estimate S naught U in hk plus 1 z rho bar is less than or equal to now w chi plus of a of u hk plus 1 z rho plus w c rho and then chi minus a c rho of u hk plus 1. But by what we've just proved, this is now bounded in the chi plus a norm of u hk z rho, and then this is bounded in the chi minus a norm of hk z rho bar. Okay, and of course this is applied for each t, right? So with the spectral decomposition, each for each t, and so it's easy to see just like from before, because chi plus of a, of course, commutes with so we know that chi plus of a is, so first of all it commutes with the t derivative, and it commutes with the operator a, which can generate the hk norm that we obtained, that this is now going to be equivalent to u in hk z rho of p. And by density, we have that S rho maps hk z rho bar of e to hk plus 1 z rho bar of e. So this also hopefully justifies to you now why we call this maximal regularity, right? So somehow the S naught is really a potential. We've already seen in the last time in the lemma that it's an inverse to the left, and it's a potential, so it's actually boosting up regularity. And we want to now obtain information about D from S, okay, or D naught. So for that we have to define a particular boundary condition, right? So define the boundary condition B naught as equal to chi minus a of h half on the one side of the boundary for 0 cross, so this is the real boundary of E, cross chi plus of a h half for the fake row part of the boundary. Okay, and then define hk of z rho e taking values in B naught to be equal to the u in hk of z rho, oops, there's a closure here, e such that u naught u rho is in B naught. Okay. So now comes a very, very fundamental result. Okay. Theorem. So let dom d naught z rho in L2 of z, oops, d naught max denote the maximal domain of d naught in L2 Z rho of E. Okay, so not on the infinite cylinder, but just on this finite cylinder, right? So maybe actually I'll take that out of the theorem and say we'll just fix the notation. So let's just fix some notation here. All right, so now let's write out the theorem. The following hold. So for all u in DOM D naught max Z rho bar with chi minus of A u rho equals 0, okay? I minus S naught sigma naught inverse D naught u of t, which is what? So u of t dot, I should say, which is what? So this is equal to I minus S naught partial t plus A, right? That's what this is, ut dot. So this is exactly equal to e to the minus t modulus A chi plus of A applied to u naught. Okay, so the obstruction for S naught to be a right inverse. So this is saying that the obstruction for S naught to be a right inverse for D, sorry, left inverse. I always get right and left mixed up. So for S naught to be a left inverse for D is precisely, the obstruction for that is precisely this positive part, right? So it is the initial values of the data that fall into the positive spectrum of the adapted operator on the boundary. Okay. The second point is that now maybe we can see this. So for all k which are natural numbers greater than or equal to 0, D naught from hk plus 1 Z rho E taking values in B naught to hk Z rho bar of F is an isomorphism. Is a Banach space. Is a Banach space isomorphism with inverse S naught, S naught sigma naught inverse. Okay, so that's really an important regularity theorem, right? So as I mean, if we consider what happens in the case where we don't have boundary, we automatically have that first order differential operator maps the Sobolev space hk plus 1 to hk. But here, when we have boundary and we have an elliptic operator, then the same is not true. It's only true if we choose the boundary conditions in an appropriate way. So, so the first thing gives us a very explicit description of the obstruction for S naught to be a right inverse, and the second tells us when we can invert the operator D naught on which Sobolev scales, right? Remember the maximal domain of the operator. So this maximal domain has a piece. So if we take the trace, it's going to have a non-trivial piece in H minus a half. So there's no way we could expect nice regularity properties for an infinite number of infinite dimensional subspace of DOM D naught max. So this is really ruling out the parts where we can expect nice regularity, right? And that's more or less away from this chi-plus part. Okay, so let me just also remark something here. The assumption, so we made an assumption here. The assumption chi minus a of u rho equals 0 is always satisfied in application. Okay, so as we said before, so let's recall from before, as we said before, the boundary rho cross partial m is the fake boundary. Okay, i.e. we have introduced it artificially. So usually we use cutoffs to consider u such that the support of u is contained in this row, right? So we're given, so the row comes out of geometry, then we use some cutoffs so that the support of the things that we have to consider for boundary value problems doesn't touch row. And so this in particular implies that, well, this implies in fact that u at row is equal to 0, and in particular chi minus a of u at row equals 0. Okay. Without this assumption, the formula would contain the term e to the minus rho minus t modulus a chi minus of a u of rho, right? But it's somehow harder the term on the right hand side of 1. So I didn't include it here because that's really distracting, right? We don't really care about what happens on the end of the row end, because this is always just something artificial in application. Okay, so let's prove this, right? So let's prove this. So how do we prove this? So are there any questions up to this point before I get into the proof of this? Okay, good. So let's first let's decompose this and write d naught of u equal to d naught of u plus d naught of u minus, where u plus minus is equal to chi plus minus of a of u. Okay, so this is maybe just to emphasize, maybe I'll put a u plus minus of t here. So this is really being applied for each t, right? Okay. So what happens now? So that implies the following. So sigma naught inverse d naught, which is dt plus which is dt plus a, this is precisely just going to be equal to partial s u plus minus of s plus minus of modulus a u plus minus of s, right? Since a is equal to modulus a signum of a. Okay? All right. So S naught sigma naught inverse d naught of u. It's just going to be the first term of our expression, because the second, because applying this for the u plus part, the chi minus of the u plus is 0. So the second term doesn't appear here. So this is e to the minus t minus s modulus a. And what do we have here? So now we so now we apply partial s u plus modulus a u plus so there's a s here, ds, and so this requires a little bit of Banach valued fundamental theorem of calculus, but this is not hard to do. So this is 0 to t of partial s. It's the same proofs as in Rn or R that work, because we're just looking at maps from R into the real line. So this is s ds. Okay. Well, actually, this doesn't require that. This is just straight factorization, and then there's a so this is equal. So there's a Banach valued fundamental theorem of calculus. Okay, so then this allows us to write this as e to the minus t minus s modulus a u plus, and we evaluate it at s equals 0. Well, shit, there should be an s here, and s equals t. So what's that? So this is going to be u plus at t minus e to the minus modulus minus t modulus a u plus at 0. Okay, good. Okay. So what's this? So this is the identity, right? So if we now multiply by a negative sign and pull the u plus across, this gives us that I minus s naught sigma naught inverse d naught of, right, with brackets here, of u plus is precisely equal to e to the negative t modulus a u plus, well, I'll write it just here, chi plus of a u applied to 0. Good. And then we do a similar calculation, right? Similar calculation yields together with chi minus of a u rho equals 0 yields that actually it's an inverse, right? We get that I minus s naught sigma naught inverse d naught of u minus is actually equal to 0. And then together obtain 1. Okay, good. So for 2, so proof of 2.
Something went wrong. Please try again.
If we have u in hk plus 1 z rho bar e b naught, then what do we have? We have chi plus of a of u equals 0 and chi minus a u at 0, sorry, at 0 equals 0 and at rho equals 0. Okay, And then that tells us that U is equal to S naught sigma naught inverse D naught U from 1. So since sigma naught is smooth, so this is a smooth section of the endomorphic. So this is a smooth and invertible, we have that D naught maps HK plus 1 Z rho bar E values in B naught to HK Z rho bar F isomorphically. Okay, good. So how are we doing with time? So I think we can get through the last part of all of this regularity, right? So now we have understood the mapping properties of D naught, and now we want to understand regularity up to the boundary for the problems that we have. So theorem. Regularity up to boundary in Z, right? Z is the infinite cylinder. So that means we want to characterize, right? So we characterize the maximal domain. So D naught max, so this is the maximal domain in the cylinder, intersect HK plus 1 lock ZE. So what is the characterization of this? So this is equal to the set U in DOM D naught max such that D naught of U is in HK lock of ZE, and we want chi plus of A of the restriction of U to the boundary to be now in HK plus a half. So all of the regularity comes from the positive part of the spectrum, right? So any and we see that. I mean, you can impressionistically see that this is the case if you are if you're on the for the case K is equal to 0. Okay, so any obstruction to H1 regularity is purely contained in the positive part. So so as a remark, so let me just say as a remark before we prove this. So remark, note that this is equivalent to saying that U in DOM D naught max such that D naught of U is in HK lock ZE and U restricted to the boundary is in HK plus a half partial ME, i.e. the negative projector having enough regularity on the boundary is automatic. Okay. Okay, good. So let's prove this. So let U in DOM D naught max intersect. So one direction is easy, right? It's clear to see that, okay, so this is the easy direction. So suppose we have K plus 1 lock ZE. So so from the trace theorem, so we can always localize. Okay, so let me write this out. So fix some rho less than some finite rho, and let eta let eta be a smooth cutoff function in z in 0 to rho, such that what? So such that eta t equals 1 when t is in 0 to half rho, and 0 when t is in, say, 3/4 rho to infinity. Okay, so it's easy to find, and so then u is equal to eta u plus 1 minus eta of u, but 1 minus eta of u restricted to the boundary is 0, right? So this part is in the minimal domain of the operator, so we don't have to worry about that. So interior regularity, so we have, okay, let me explicitly write that. So eta u restricted to the boundary is equal to u restricted to the boundary, and since eta rho is 0, we have an interior regularity theorem, right? Elliptic regularity yields 1 minus eta of u is in hk log of e. Oh, sorry, d naught of this is in hk log of e. Okay. So now let's take v equal to eta of u. This is clearly in hk z rho closure e. And also we can see that trivially we have that v restricted to partial m, which we said, so u restricted to partial m, which we said from before is v restricted to partial m, is just by the trace theorem k plus a half on the boundary. So in particular, we have that chi plus of a u restricted to the boundary is in h k plus a half partial me, because remember, these spectral projectors are bounded on all Sobolev scales, right? That's something that we said right at the start. And so it's not hard to see, it is not hard to see that d naught of v is in hk. Okay, z rho e. So that's one direction. That's actually the easy direction. Now let's prove the converse, right? So this proves maybe this direction, right? So this is this direction. So now let's prove the converse direction. Okay, so let u be in dom d naught max, such that d naught is in the hk lock ze, and this restriction to the boundary is in hk plus a half on the boundary. Okay, so let's assume this. Using cutoffs, so using cutoff as above, okay, so using cutoff as above, we have that 1 minus eta of u is in dom d naught min, and the support in fact, more than that, 1 minus eta of u is supported now in the interior of this z. And since D is elliptic, what do we have? So since D is elliptic, we have D naught of 1 minus eta of u is equal to D naught of u minus D naught D eta of u minus eta D naught of u, and this is all in HK log. Okay, so the support property then means that interior regularity then implies that 1 minus eta of u is in HK plus 1 lock. So this is in lock ZE, and this is in ZE. Okay, so that's not the interesting part actually, right? That's the easy part because we're staying away from the boundary. So the interesting part is what happens at the boundary. So set as before v equals to eta u. So we have v restricted to the boundary is equal to u restricted to the boundary. Or maybe I should say v at 0 is u restricted to the boundary. That's the interesting part. And v at rho is equal to 0. So what do we have? So we have that v of t is equal to s naught sigma naught inverse d naught of vt plus e to the minus t modulus a of v chi plus of a of v restricted to 0. Okay, so I should just say here that, remember, by hypothesis, this is now, well, okay, this part isn't in there. Sorry, I'll talk about that in a second. Okay, so let's set this equal to v naught of t plus v1 of t. Okay, so so what do we have here? So first of all, we have, so from lemma we have that S naught maps HK Z rho of E to HK plus 1 Z rho, closures of E. So since we assume that D naught of U is in HK lock of ZE, that implies that D naught of V is in HK of Z rho of E. Right? The sigma naught preserves Sobolev regularity, so that tells us and sigma naught inverse maps HK Z rho E to HK Z rho E. So we get V naught in HK plus 1 Z rho bar E. Good. So that's that part. So now we have to think about how to prove the other part. So that's really where the interesting content is hidden. So again, so let's now take an L in the interval 0 to k plus 1. So again, we recall the theorem that, or the lemma that allows us to understand these Sobolev scales in terms of partial t and modulus a. So we fix such an L and we compute. So let's take partial t L modulus A k plus 1 minus L of V1 L2 Z rho squared. Okay, so what's this equal to? So this is now, the partial t and the A commute. That's the advantage of moving to the model operator, right? The model operator is t independent. So we can commute. Good. And so then what happens, right? So now we are applying, so what's this now? So this is going to be, there's a power of L here. So this is modulus A k plus 1 minus L partial t to the L e to the minus t modulus A chi plus A V0. Okay, that's what we have, squared L2 over Z rho bar. So now what happens? So now we produce L copies of this, right? So now we get something like modulus K plus 1 minus L modulus A to the L e to the minus t modulus A chi plus A V naught squared L2 over Z rho bar. Okay, so now we have the full k plus 1. So we have modulus A k plus 1 e to the minus t modulus A chi plus of A V naught squared L2 over Z rho here. So actually this is why maximal even if we use maximal regularity only alluding to the fact that we're on a Hilbert space and we have a omega sectorial or bisectorial operator with an angle less than pi on 2, this is where the quadratic estimate still comes in, right? So here, what am I going to do now? I'm going to commute, so I assume that chi plus of A V naught actually is in, so remember the assumption is that this is in k plus a half, in hk plus a half. So let me take that across, so let me leave a power of a half here, which means so this integral is now equal to what? This is 0 to rho of the L2 integral on the boundary. So I'm going to add t a half here. Now I have e to the minus t modulus A, and I'm going to commute across modulus A k plus a half power here. So this is really a beautiful expression, right? This tells you explicitly, it doesn't get any more explicit than this. So this is the L2 integral on the boundary and a dt. So this shows you explicitly where the derivative loss is. So you can really reinterpret these trace theorems from a H infinity functional calculus point of view. And so what does the H infinity functional calculus tell us? So it tells us that, I'm afraid no, it's okay. So it tells us now that this integral is going to be, first of all, I can replace the rho with infinite. So, so this tells us that this estimate is now going to be bounded by modulus A, k plus a half, chi plus of A, V naught, squared L2 on the boundary. Sorry, there's a dt on t here. L2 boundary, dt on t. So that's what it tells us, right? So this is the H infinity functional calculus. That shows its beautiful face again in this theory. Good. So then this is precisely now the comparable to the HK norm over the boundary. Sorry, HK plus a half norm. Sorry, K plus a half norm over the boundary. Okay, so, I mean, this then tells us, so what does this tell us? This tells us that V1 is in the intersections of the domains L equals 1 to K plus 1, or L equals 0 even, to K plus 1, of L2 of 0 to rho, with taking values in domain partial T L modulus A K plus 1 minus L, which is equal to H K plus 1 Z rho bar E. Great. So that's good. So that means that V now, which is equal to V naught plus V1, is in HK plus 1 Z rho bar E. And so this tells us that U is in HK plus 1 log of Z over E. So that's the proof. Good. Okay, so let's see. So maybe I'll just finish with one last thing. So let R naught 0 be the constant in the operator reduction lemma. Then the following, so let R naught be the constant in the operator reduction lemma. So then I want to just say, so we have, there exists some constant such that for all U in C infinity, C in Z R prime of E with, so closure E with chi plus A of U of rho equals 0, and the support of U in 0 R prime R prime cross partial M, we have that U in the H1 norm now on the on this ZR prime squared is less than or equal to this constant C1 partial T plus A of U squared plus now the U squared here. Okay, so this is a direct consequence. So this is just a direct I should maybe have called this a corollary, right? So corollary, consequence of previous lemma. And up to this point, we have really just, in the considerations, we've just used the fact that the minimal extension, the minimal domain of the operator is contained in H1 naught lock. But this immediately gives us that the domain of D naught min is equal to H okay, so this is contained in H, I have to be careful as to how I say this, so this is contained in H1 naught lock, I guess space. Well, actually, I'll mention that next time. So this is not so important, but the point is that you can see. Okay, so okay, no, I'll write it. I'll write it. So domain of D naught min now consists of H10 lock, right? So the space is bad. So this is the U in H1 lock such that U are restricted to the bound. So yeah, U restricted to the boundary is 0. Okay, so that's really where the domain of D naught min sits. So when it's the finite cylinder, well, okay, so yeah, I'll just leave it at that actually, because I think it's technically a bit complicated to describe that, but yeah. Okay, so next time we will move beyond the questions to do with the model problem, and we will start looking at the general operator and show how to move all of these results to the general operator. Okay, thank you very much. So are there any questions? The first lemma where I added the t's. What does that mean? Scroll to the, yeah, okay, so we can go to the first lemma. Here, you mean? Yeah, so also I should just also say that this is I'm being a bit naughty here when I write this, right? So so this should really be moved. So this is really you know, L2 sections. So this should really be L2 sections on 0 row, mapping us into this Banach space, which is the domain of all of these things. Okay, that's the first thing. Well, this is the HK space. Yes, so it's really the L2 space mapping into there, right? And then the next lemma is this lemma which shows sorry, this shouldn't be U. This should just be U. Oh, yeah, this should be U. It's just that I'm applying with the H1 norm here with V equal to S naught of U, right? So that's not a V, that's a U. No, the lemma just talks about the mapping This V is just reminding us what how the H1 norm can be written in terms of the lemma that I just gave before. This is just saying that the norm of V in H1 can be written in this following form. Yes. I mean, not in the data, but I'm just reminding what this integral is. I mean, here, I'm applying the chi plus of A pointwise to the U of t, right? That's what we get when we get the maximal regular, yeah? When we get yeah, when we get the, so maybe I should just say that for the benefit of others. So when we get the maximal regularity bound, remember, I mean, this is really on the cylinder. So we are now applying this datum, so chi plus of A U is applied on each slice to U, right? So one can think of the cylinder as really something like a spectral decomposition of the boundary, but extended into the cylinder now. So each slice is being decomposed by the spectral projectors. And we can do that because each slice here is isomorphic or can be identified with L2 on the boundary. Okay, so are there any other questions? You mean to here to the this Sobolev space? You mean, or yeah, sure. Yeah, that's true. That's true. I mean, a priori, we do really need, for the T's, we really need that, but for the A's, we don't have that, right? So let me think about how to best write that when we, I mean, the problem is that when I'm writing the, you're right, when I'm writing the domain partial T, K minus L here, then I'm already on the cylinder. That's what you're saying. But then the modulus A's are not in the cylinder. So, yeah, maybe this is bad notation to write it as L2 here because that's already present in this. But then we should just, maybe I'll make a remark to say that the modulus A here is the action of the modulus A now. Seeing this as an operator on the cylinder is really just application point wise for each T. Maybe I should say that, yeah. Yeah, thanks for that. But here, of course, so maybe I can fix that by instead writing explicitly here that this is really the integral now on Z rho. Right, that's really the L2 integral on Z rho. Yes. Okay, so I hope that fixes it. Okay, so if there's no other questions, I will hang up. Thank you all for the attention. Yes, will do. Thank you. Bye.